Yeah, that stand's becoming useless.
Huh?
The stand,
It may come
mic
in
stand's
useful, it
like
may
useless.
trip me, I don't know, we'll see. We'll see. All right. I want to be out here a little bit better. Okay. So I'm Brian Jameson, and I work in guidance, navigation, and control at Marshall Space Flight Center. My co-authors are Mike Hannon, Jim Cady, Juan Orphy, and Nick Olson. And this past year, we've been working in a project where we were doing a pilot evaluation of model-based design tooling for guidance, navigation, and control flight software. Let's see if I can, is there somewhere that this has to point? Okay, I'm pointing it back there. Okay. And I'm pointing it back there. There it goes, okay. Okay, so first of all, I haven't heard this term come up too much, I don't think, so maybe or maybe not you know what model-based design is, but that's basically just you're using the model in the design process. And so what we're seeking to do here is we're seeking to systematically use models throughout the development process for requirements, design, analysis, simulation, verification and validation, and documentation, whereas a more document-driven system would be kind of the older method of doing it. And so we want to do that to automate our system and have a concurrent design process so that we can minimize human error, of course. And so probably many of you have seen this kind of a diagram where we have kind of the verification and validation V diagram over here on the right, where we want to iterate quickly and do small iterations each time we need to step through any of these parts of the verification and validation. So some of the improvements offered by model-based design include efficiency improvements by automating a lot of the aspects of requirements testing and documentation. And we've used a lot of MathWorks model-based design tools in our work for this evaluation. And one of the big advantages of that was that it includes model visualization that's naturally a part of the guidance, navigation, and control development process. And so since we're working with guidance, navigation, and control every day, and that's what Simulink is all about, that works well for us. So just a little bit of background pieces of information as was the previous one slide. This one, so if you, I don't know if any of you will recognize any of these slides that are shown, but Dr. Karen Gundy-Burlett presented here at this workshop about 3 different times in the past relative to the LADEE mission experience and the model-based design that they were doing that was at a less developed stage of the MathWorks model-based design tooling, but they had good experience with that. She said that compared with using model-based design, hand-coding the flight software would have taken longer and made collaboration more difficult. And so there was a lot of advantages that they found to this. I've got a picture. I'll let you read through the details later if you want. But basically, one of the advantages was that we weren't just throwing the model over the wall to the flight software folks. So I'm sure a lot of you would probably appreciate that. Hopefully we do a good enough job as we're going through this process to eliminate some of that. But here's an image, if it'll come up, back there. Oops, wrong way. Okay. Here's an image of the spacecraft, right? Right? Okay, we're going the wrong direction. Sorry about that. And there it is. Okay, so it flew in 2013 and then was disposed of on the moon's surface in 2014. But they had a good experience with that. And so we were wanting to investigate a little bit more about that and implement some of that process for our procedures in the group that we were in. I will tell you a little bit more about that and that mission in a little bit. So, of course, MathWorks has done a lot with model-based design tooling. There's a poster here, but it's been produced by MathWorks. In fact, I can see the person who wrote the poster, but he worked with others, including some from Marshall and other places, I suppose, to produce that, and they've kind of synced that up really well with their design, with their tooling. So this process that they've developed covers a lot of 7150, including software requirements, design, implementation, and testing. It doesn't include things like architecture requirements and project management requirements, but pretty much everything you can, as I understand, with software requirements. And so one of the things that we've been doing as we've been implementing this model-based design approach is we've been meeting and consulting with the people here at Marshall Space Flight Center, the software people here, to make sure that we're not kind of getting out of sync and doing our own thing without, or that we're making sure that our process will work with theirs. Okay, I'm pointing it back there. And there we go, okay. Okay. All right, so our project that we were on was called the Viper Lunar Lander. I'll tell you a little bit more about that in a bit. But we were using this project as a pilot project for doing model-based design of our guidance, navigation, control flight software development. So our goal was to apply this model-based design approach and tooling to condense our schedule, to reduce needed resources, and to improve the quality of the GNC flight software. So some of the expected benefits are that it would facilitate requirements, implementation, verification, and automate testing, several parts of testing, coding standard enforcement, code generation, static code analysis, and report generation. And in total, it would establish a highly automated, disciplined process that would allow repeated testing of the system throughout the design process. Now, I've got a picture there of the Viper lander. Just maybe a month or so ago, NASA put out a press release about the Viper rover, which so basically the plan is that with NASA going to the South Pole, I shouldn't say back to the South Pole, but going to the South Pole of the moon, they're planning on sending a rover there to map water ice and where that would be there at the South Pole of the moon. And so they released that, and this lander had been in development for delivering that rover. You can see it's kind of a pallet style. The solid rocket booster on the bottom would drop away some 8 or 10 kilometers above the surface, and you'd basically have a pallet that'd be landing on the lunar surface for the rover to drive off of. Unfortunately, at least in my view, but NASA decided they wanted to deliver that rover to the surface using the commercial lunar payload services contract. So basically using a company to do that. But then shortly after, or even more recently, I should say, here in the last few weeks, they released basically the design of this lander to the public so that they could bid for, we'd like to use these elements of it, or there's a white paper on it and things like that. So a lot of that's available now. I'm probably missing something that I wanted to tell you about that, but I guess you can answer questions if I did. Okay. All right, so kind of a core piece of our guidance, navigation, control development system is what we call affectionately GLASS. That I don't know that that's meant to imply that it breaks all the time. I think that's maybe more of an implication of it offering some better insight into our process. I don't know, I'm not the one who named it, but basically it stood for Generalized Lander Simulation in Simulink. It now handles more general spacecraft. It's a 6 DOF. And so it's very well designed. Nick's the one who's kind of the lead on that, and it's very modern and flexible and user-friendly. He's done a great job of updating it or ensuring that each time MATLAB releases a new version, that it's quickly checked out and make sure that it'll work for that one. So we're kind of up to date so far on being able to run in the most recent releases of MATLAB. So that's one of the nice things about it. And so it basically has this common core that has the dynamics in it, and then we can interchange the vehicle-specific plant models and the vehicle-specific guidance, navigation, control models into that core, or with that core, in glass. And of course, there's several advantages of this, including that we can do autocode, and that it interfaces with a lot of MathWorks tools. So there's a lot of capability there. So to take a high-level view of our process. So starting from the real world, of course, we want to use glass to model the real world and to produce our guidance, navigation, and control flight software. And so we have where we can check the requirements using Simulink requirements and Simulink test. We can, we're of course modeling with Simulink, and we can do code development there, and we can use Model Advisor in that process. We can also automatically generate reports, or do customized reports using the report generator. We can do Simulink, we can do unit testing using Simulink model and code coverage testing, and we can do autocode, of course, to be able to do the code testing using the embedded coder, and we can use the polyspace tools to do static code analysis, and all of that with the goal of producing quality autocode for our guidance, navigation, and control flight software. So looking a little bit more at the kind of the first half here is what we've kind of gotten implemented so far in the process. It works out something like this. We started with our requirements in Excel in a spreadsheet up here, upper left. And so we can basically put our wording in there. That's kind of the blue column that you'll see there. And our specification values there in the kind of the orange column. And we can combine those using a simple formula. And so then we can have our requirement specifications that we're going to import directly into Simulink requirements to track. And so of course we can, well, I'll get back to that. We can also take the values that we've specified there into a Simulink data dictionary and use those in Simulink test and in the test harnesses and so forth, and tie those results directly in with Simulink test and its tracking of how we're doing it, following those requirements. We can also do unit testing and model coverage testing, and we can generate reports for that. And then of course all of that can be updated through a simple scripting and iteration to make sure that everything stays in sync there. Just to kind of walk through this, I produced a video to show you this, but there was some concern that I might not be able to email it to all the people that it had to get approved by, and so I now get to walk you through it. But basically, this process that I'll show you over the next 6 or 7 or 8 slides is basically a process that with 1 or 2 clicks of the mouse can update several things in the whole process. This is a rather simple example. We realize there'll be more complicated ones, but this one's kind of where we got with our initial start, and then there's a lot of stuff that kind of goes on underneath, or is potential underneath. And so with our spreadsheet, we've got our requirements here, and we're just going to go and we're going to test that. But then with these results, we can see here, in this case, we were just testing the 5 requirements there that you see in red or green. 2 of them passed and 3 of them failed. And so I wanted to, I guess I was just going to mention the irony that I'm clicking the mouse more time, or he is, than I would have to, for this whole update process, just to show you this because of the lack of the movie, just for the file size issue. But so with just 1 or 2 clicks, we can do this whole process. So we can see where we've got the failures. We can look at the cases we've got. In this case, we were doing Monte Carlo iterations of 200 apiece, and we were doing some landing precision tests. And so we can see where those failed. We can expand that out. That'd be the next slide. Am I in charge of that, or is he? I don't know yet. Okay, so we can just expand that out, and we can look at details of those iterations. Next, there it is. Okay, and so we can dig into the details of those iterations and look at where we failed. In this particular case, our landing lateral speed was a little bit too high. And so for this simple example, we're just gonna go to the next slide, and we're gonna update some of the parameter values in our requirements. One of the things that I created in here was just a rather simple macro with Google's help to create highlighting and a note there in the spreadsheet to say, you've updated this, make sure that you're going through the process in the correct way to kind of get it through the system. Because it was a case, there'll be 1 or 2 of you here maybe who were, yeah, I'm seeing at least one familiar face who was there when I presented some of this before, and I did this and failed to go through the wrong way and broke the system, which helped me learn a thing or two. But basically, so now it's all automated, so that one, it's going to do this highlighting so that I'm careful about not about how I update it. I follow procedure as given on this red tab down at the bottom you see. But then with just a simple run of this script, just clicking on the button, clicking on just 1 click there, it's going to clean up my spreadsheet for me. It's going to import everything into the system. It's going to put those values now in the data dictionary for the simulation. And so this one thing I failed to mention earlier is basically this is doing it this way is allowing us to have a single source of input for all of our values for requirements testing. We're not having to put them into Simulink requirements and into the data dictionary separately. We're just importing them from here into both. And so just retesting that, we can see that we've passed, or essentially passed all of them that had the last 3 yet to go, but they did all pass, trust me. But basically that's the video, and so we can see that they all passed here in Simulink requirements. So that's a little bit of a quick run through it. One of the other things that same script does is that it can produce reports. Of course, there's more generic reports available, but you can also customize some of your reporting. So that's what we were doing here with some. And then one of the other benefits of model-based design is the auto-coding, at least for us that is, since we're not super experts on some of that C++, like a lot of you guys are, I'm sure. But then it enforces some of those coding standards and make sure that we're consistent there. And of course, that's used by a number of folks. Now, just a quick detail, I guess a little bit more detail on that one. Basically, we've got our model here on the right, and the code that's produced for it is there more in the center, and along with the report, the coding report, where you can dig into the details. You can see, you can't read it from where you are, I'm sure, but basically you can see that a lot of your commenting from your MATLAB scripting can go directly into the coding here to clarify what's going on and just make sure everything's clean for review. And then one of the nice things is that you can link between the model and the code, and so you can review some of those details a lot easier. Of course, we want to do coverage testing as well, and so there's linking there between the modeling and the code. and you can do that between, well, I should say, between the model and the test, and the code and the test. And so that eases repair of it and everything. Of course, we want to do static code. Okay, we want to do static code checking as well, and so we use the polyspace. The plan is to use the polyspace tools for that. We kind of just got started into that when MBD got in the way. OMB, whatever that's. All right, when the project was canceled, basically. That reminds me, one of the things I wanted to tell you was with this being, as we were developing this, we realized it's not, we wanted it to work for plenty of other programs, and one of the plans at this point is to use it for possibly MAV, the Mars Ascent Vehicle that's been mentioned here. But that's kind of one of the things that with our developing this was to develop a process that'd be useful across any program. So with that, of course, we want to check the static code analysis. The image at the right is of the Ariane 5 just moments before it began to break up, and then it's activated its self-destruct mechanism. You can kind of see that there's maybe I'm going to call it a 30-degree angle between the thrust vector and the rocket. About 2 seconds before this, they were pretty well lined up, but basically because of an arithmetic failure or overflow, the system failed. This is about 60-some seconds into the flight, and so it destroyed itself. So that's probably one of the most famous examples of you got to be careful with your code and doing static code checking. So just a few details here. I won't go into all of them, but basically, rather than doing the traditional document-centric development, we're wanting to do this model-based design approach to automate a lot of things in the process. Next. Okay, so basically we're wanting to fit a lot of pieces together of the puzzle to automate the process, to do testing, to do auto-coding, and to do reporting. And I'll fit all these pieces together to have a highly automated system. In summary, we've developed a preliminary process to generate quality guidance, navigation, and control flight software code using model-based design tools as well as Excel. And we've also had our initial discussions, and we plan to have continuing discussions with the flight software people here at Marshall to make sure that we're working together. Our goals are to increase development speed, to reduce the amount of manual tasks we have to do, to improve the traceability from requirements to the model and code verification, and to ultimately produce high-quality GNC flight software. Are there any questions?
So you had talked about running polyspace or other static analysis tools on the generated code to make sure it complies with coding standards like MISRA, JSF, etc.
Yes.
Most of these standards were designed to catch the sort of errors that humans make when handwriting code. What sorts of errors have you typically seen in generated code, and do you think that perhaps different standards would be useful to check against?
Okay. Unfortunately, that was kind of one of the stages that we didn't really get very far to, nor was I the one who was working with polyspace as much. Because of the cancellation of Viper, we're kind of stalled out on that. I know they had done some use of polyspace. Jim Cady was the one who was working with that, and I think Nick as well. And I know they ran through the control portion of the code for some initial assurance on things there, but I don't know how much far. I don't think it got any farther than that. But if you want to contact them and ask them more details, you probably could.
Thanks for that presentation. Very interesting. Just one side remark. I think you wouldn't have caught the Ariane 5 problem with your approach, because the overflow was a result of a lot of other problems which you would not have discovered with autocoding and polyspace.
Okay, I'm not an expert on that. I know MathWorks frequently, at least I believe they cite that as something that polyspace would have caught. I
can discuss
apologize
about that later.
if I'm incorrect on that. I did read a little bit about that, and that was some, yeah. I guess you could probably talk with them for more details than I would know.
Other questions? Okay, great. Thank you.